In the late 19th century, when the scientific world still clung to the certainties of classical physics, a child was born in the quiet city of Copenhagen who would one day challenge the very structure of that certainty. The year was 1885, and Europe stood at the threshold of a technological awakening. Telegraphs hummed across continents, electric lights began to pierce the darkness of old streets, and the dream of understanding nature through mathematics seemed almost complete. Yet, within this time of confidence and precision, something profound was missing. A deeper truth about the invisible heart of matter. It was into this world that Niels Henrik David Bohr took his first breath, unaware that his own mind would one day become the bridge between the known and the unknown. The Bohr household was one of intellect, warmth, and quiet thought. His father, Christian Bohr, was a respected professor of physiology at the University of Copenhagen, a man whose research into the nature of gases and oxygen transport in blood shaped young Niels' earliest fascination with science. His mother, Ellen Adler Bohr, came from a wealthy and cultured Jewish family known for their influence in education and social progress. Between his father's rigorous scientific curiosity and his mother's philosophical grace, Niels grew up in an environment where ideas were alive, discussed, debated, and questioned around the dinner table. The young boy absorbed this atmosphere like light into glass. In the late evenings, when the gas lamps flickered and the Danish winter pressed against the windows, Niels would sit quietly, listening to his father explain how the lungs exchanged invisible particles of air, how chemistry and physics intertwined in the breath of life. To Niels, these were not just scientific facts. They were glimpses into an unseen universe that existed beyond touch or sight. His curiosity began not with the atom itself, but with the realization that reality had layers, that the visible was only the surface of something deeper, stranger, and infinitely more beautiful. At the Gammelholm Latin School, where Bohr was educated, he was known not for being the most vocal student, but for his extraordinary ability to think beyond the textbook. Teachers noted his patience and his quiet intensity, a mind always searching for underlying principles rather than memorizing established truths. Mathematics came to him like a language, but it was physics that gave him purpose. The laws of motion, the mysteries of light, and the puzzles of energy ignited a sense of wonder that never left him. Unlike many students who sought answers, Bohr seemed more interested in the questions themselves, questions that opened doors rather than closed them. His first experiments were simple, almost childlike in their curiosity. In his father's laboratory, Niels and his younger brother Harold would spend hours tinkering with instruments, measuring reactions, observing how liquids behaved under different temperatures or how light refracted through glass. There was no formal plan, no grand hypothesis, just the joy of exploration. What fascinated Niels most was not what science already explained, but what it could not. He noticed that even in the most carefully controlled experiments, there were patterns that refused to fit. Small deviations, strange irregularities, and inexplicable results. They whispered to him that nature had secrets still untold. As he grew older, this fascination matured into a quiet obsession. By the time he entered the University of Copenhagen in 1903, Bohr was no longer merely curious. He was driven by an inner need to understand the world on its most fundamental level. The university itself was a hub of learning and discovery, alive with the spirit of inquiry that characterized the turn of the century. Great scientists like Lord Kelvin and J.J. Thomson were redefining physics with their theories on electromagnetism and the structure of the atom. Yet to Bohr, something about these models felt incomplete. He could not accept that the atom, the very building block of everything, was merely a tiny solar system of particles following predictable orbits. There had to be something more subtle, more mysterious at play in 1905, when Albert Einstein published his papers on the photoelectric effect and special relativity. Bohr was among the young minds who read them with astonishment. The idea that light could behave both as a wave and as a particle electrified his imagination. If light could be quantized, if energy itself came in discrete packets, then perhaps matter, too, was not the continuous, solid thing it seemed. Perhaps at the smallest scales, reality itself was grainy, jumping between states in ways classical physics could not describe. This idea stayed with Bohr, like a spark in the back of his mind that refused to go out. Outside the lecture halls, Niels lived a modest and quiet life. He preferred long walks by the Copenhagen harbor, watching the sunlight scatter across the water. He would often pause, lost in thought, seeing in the ripples of the sea a metaphor for the mysteries of energy and motion. He was known among friends for his kindness and humility, but beneath that calm exterior lay a restless intellect. He was not content with accepting knowledge. He wanted to understand why it existed at all. His conversations with fellow students and his brother Harold, who would later become a renowned mathematician, often turned into deep discussions about reality, time, and the limits of human perception. When Bohr began his doctoral research in 1909, he chose a subject that reflected his deep curiosity about the intersection of physics and philosophy: the theory of electrons in metals. Though the topic might seem technical, for Bohr it was a window into the behavior of the unseen world. He performed meticulous experiments, analyzing how electrons moved and interacted, and in doing so he began to sense the inadequacy of classical models. They worked for large systems, but when applied to the atomic scale, they broke down. The equations failed to capture the strange, discontinuous behavior that nature revealed under the microscope of mathematics. Bohr felt the tension between the visible and the invisible, between the certainty of numbers and the uncertainty of observation. Copenhagen, in those years, was a place of quiet progress. Steamships lined the docks, carriages clattered over cobblestone streets, and the scent of salt air mixed with the distant hum of the city's awakening modernity. Yet inside Bohr's small study, a different kind of revolution was taking place, one of thought. Late into the night, he would sit surrounded by papers filled with equations, scribbles, and questions. Sometimes the candlelight would flicker across his face as he paused, staring into space, as though listening for an answer from the universe itself. He believed that if he could just look at nature from the right angle, the chaos would resolve into order. That faith, quiet but unshakable, guided his every step. Bohr's mind was not only analytical, it was deeply philosophical. He often reflected on the nature of scientific truth, wondering whether the human mind could ever fully comprehend the fabric of existence. He once remarked to a friend that every great advance in science came not from solving a problem, but from seeing an old problem in a new way. To him, the world was not something to be conquered or explained away. It was something to be understood through humility and imagination. That balance between logic and wonder would later define his entire approach to quantum theory. During his time at university, Bohr's reputation as a thinker grew rapidly. Professors noted his unusual ability to blend abstract reasoning with physical insight. He could take a complex theoretical problem and, through calm reflection, find the simple truth beneath it. But Bohr was never arrogant. He often questioned his own conclusions, aware that every explanation opened a new mystery. His notes from that period show a mind in constant dialogue with itself, doubting, testing, and revising ideas. In one margin, he wrote a simple line: "Perhaps the atom is not what we think it is." That single thought would become the seed of a revolution. When Bohr completed his PhD in 1911, his work received praise for its originality and depth, yet he was unsatisfied. He felt that he had only touched the surface of a vast and hidden truth. To pursue it further, he traveled to England, hoping to work under the great physicists of his time. It was there, at the Cavendish Laboratory in Cambridge, that his life would change direction forever. Surrounded by experimental physicists like J.J. Thomson and Ernest Rutherford, Bohr entered a world where the atom was no longer just a philosophical idea. It was becoming a measurable reality. The discovery of the nucleus, the structure of the atom, and the scattering of particles were all reshaping the map of physics. Bohr watched, learned, and thought, and in his mind the pieces began to fall into place. He saw that the atom, as understood by classical mechanics, was unstable. Electrons orbiting a nucleus should radiate energy and collapse inward, yet they did not. Why? This question haunted him. It was not a small technical puzzle, it was a fundamental flaw in the understanding of matter itself. Classical physics, so powerful in describing planets and machines, was powerless in describing the world of the very small. It was as though reality had two languages, one for the macrocosm, one for the microcosm, and they refused to translate. Bohr's curiosity burned brighter than ever. He was determined to find the bridge between them. His early life had prepared him for this moment. The patient curiosity of his childhood, the disciplined reasoning of his education, the philosophical questioning of his youth, all converged as he stood on the edge of discovery. Every night, as he walked home through the quiet English streets, Bohr thought of the unseen forces shaping the world, of electrons leaping, of light pulsing in quanta, of energy dancing in ways no one yet understood. He began to imagine the atom not as a miniature solar system, but as something more mysterious, a structure guided by hidden rules, quantized and discrete. It was an idea that seemed impossible, yet irresistibly true. If one were to imagine this period of his life as a scene in a film, the music would be soft but growing, strings building slowly as Bohr stands by the window, looking out into the fog. Behind his calm eyes, a storm of thought brews. The camera would zoom in on his notes, sketches of circles, equations, and faint question marks. His hand trembles slightly as he draws what would one day become the first model of the quantum atom. The light of understanding flickers within him, though the world around him still sleeps unaware. But before he could reach that moment of revelation, Bohr had to face years of uncertainty, years when answers remained just out of reach. In those years, his curiosity became his guide. He was not chasing fame or recognition, he was searching for truth. To him, the atom was not merely a scientific problem, it was a key to understanding existence itself. Every thought, every experiment, every sleepless night brought him closer to realizing that nature, in all its complexity, followed laws far stranger and more elegant than anyone had ever imagined. And so the young man from Copenhagen continued his quiet quest. His childhood curiosity, nurtured in the gentle light of his family home, had evolved into a force powerful enough to challenge centuries of scientific tradition. What began as a boy's wonder at the mysteries of air and light had become the foundation of a new science, one that would redefine not only physics, but the very way humanity perceived reality. As the curtain falls on the first chapter of Bohr's story, the world still stands unaware of what is coming. The discoveries of Planck and Einstein are stirring the waters of physics, but the full storm has yet to break. Somewhere, in a small room lit by the faint glow of a desk lamp, Niels Bohr continues to think, to question, to imagine. The sound of a pen scratching paper echoes in the stillness. He pauses, looks up, and whispers something only he can hear. A thought that will soon ignite the quantum age. The night air in Manchester was cool and heavy with the scent of smoke from nearby factories. It was 1912, and the industrial heart of England pulsed with invention. Inside a modest laboratory at the University of Manchester, Niels Bohr stood among glass tubes, metallic instruments, and faint traces of radium dust that glowed softly in the dim light. Around him moved men who were changing the face of science: Ernest Rutherford, Hans Geiger, and Ernest Marston, each probing the mysterious structure of the atom. Yet amid this atmosphere of experiment and discovery, Bohr remained a quiet observer, a thinker who saw beyond the surface of their findings. He was not content with what they measured. He wanted to understand what those measurements meant. The Rutherford model of the atom had just been born from the famous gold foil experiment, showing that nearly all of an atom's mass was concentrated in a tiny, positively charged nucleus. It was a revelation that shattered the old image of matter as a diffuse pudding of charge. But for Bohr, this picture raised more questions than it answered. If electrons orbited the nucleus like planets around the Sun, then they should lose energy, spiral inward, and collapse the atom within fractions of a second. Clearly, that did not happen. Something invisible was at work, something that defied the tidy logic of classical physics. As Bohr gazed at the data spread across Rutherford's desk, he could almost feel the presence of that hidden principle, waiting to be discovered. Outside, the city's lights flickered through the fog, and the distant clang of machinery seemed to echo the pulse of progress. Inside, Bohr's thoughts burned with quiet intensity. He began to wonder whether the problem lay not in the atom itself, but in the laws used to describe it. Perhaps, he thought, the atom followed rules entirely its own, rules that allowed electrons to move in stable orbits without radiating energy. It was a daring thought, one that bordered on heresy to the established physics of the day. Yet Bohr could not dismiss it. He returned to his quarters each night, sketching models in the margins of his notebooks, circling equations, crossing them out, then beginning again. Sleep came rarely, inspiration arrived like flashes of lightning, sudden, brilliant, and fleeting. There were moments when Bohr's mind would drift back to Copenhagen, to the serene image of his father in the laboratory, calmly explaining how oxygen binds to hemoglobin. Those early lessons in patience and precision had taught him that science was not merely about facts, it was about faith. Faith that truth, however hidden, could be reached through reason and imagination working together. He carried that faith with him now, through the sleepless nights in Manchester, as he wrestled with the paradox of atomic stability. The idea that electrons could occupy only certain allowed orbits, and could jump from one to another by absorbing or releasing discrete quanta of energy, began to crystallize in his mind. It was an audacious blending of Rutherford's nuclear model and Planck's quantum hypothesis, a union of the tangible and the abstract. One can imagine the scene as if captured by a film camera, the dim glow of a gas lamp illuminating Bohr's desk, sheets of paper scattered like fallen leaves, his hand moving quickly as equations unfold beneath the pen. Outside, rain taps gently on the window pane. The music rises softly, a piano line carrying a tone of anticipation. The camera pans to Bohr's face, calm but alive, eyes bright with the light of discovery. In that quiet room, the future of physics is being drawn in ink. By early 1913, Bohr began to formalize his ideas. He proposed that electrons travel in specific, quantized orbits around the nucleus, and that each orbit corresponds to a discrete energy level. When an electron jumps from one orbit to another, it emits or absorbs a photon whose energy matches the difference between those levels. With this simple yet profound rule, Bohr could explain the spectral lines of hydrogen, the very fingerprint of the atom that had puzzled scientists for decades. When he compared his calculated wavelengths to the observed ones, they matched perfectly. It was a moment of breathtaking clarity. The young Danish physicist had not merely solved a problem, he had revealed a new law of nature. But before triumph came doubt. Bohr hesitated to share his results. They seemed too radical, too different from the continuous physics of Newton and Maxwell. He showed his notes to Rutherford, who listened intently, his sharp eyes reflecting both skepticism and admiration. After a long pause, Rutherford smiled and said, "You may be right, Bohr. You may be right." Those words were all the encouragement he needed. Soon after, Bohr published his 3 famous papers under the title On the Constitution of Atoms and Molecules. The scientific world was stunned. Within months, the Bohr model became the cornerstone of modern atomic theory, earning him worldwide recognition. In the public imagination, this was the moment Bohr became a genius overnight, but in truth, it was the culmination of years of quiet struggle, reflection, and relentless curiosity. His discovery did not spring from sudden inspiration alone. It grew from the soil of a lifetime spent asking why the world behaves as it does. The same boy who once peered through glass prisms to watch light split into colors had now uncovered the mathematical key to that spectrum. The same young man who questioned the limits of known physics had now redrawn those limits entirely. Yet Bohr's curiosity did not stop with his own success. He knew that every answer opened a new realm of questions. His model worked beautifully for hydrogen, but what about more complex atoms? What about the strange behaviors that even his quantized orbits could not explain? As other scientists tested his ideas, discrepancies appeared, and Bohr welcomed them. Every great and deep difficulty, he once said, bears in itself its own solution. He was not afraid of uncertainty. He believed it was the essence of progress. The following years saw Bohr return to Copenhagen, where he would build one of the most influential scientific institutions in history, the Institute for Theoretical Physics, later known simply as the Bohr Institute. But before that dream took shape, Bohr continued to refine his ideas about atomic structure. He began to think of the atom not as a miniature clockwork machine, but as a dynamic system governed by probabilities and transitions. He realized that the quantum rules he had applied to energy might also apply to the very fabric of existence. This growing intuition would one day lead him toward the principle of complementarity, the idea that seemingly contradictory descriptions of nature can both be true, depending on how we observe them. At this point in his journey, the documentary lens might shift to a wider view. The world in the early 20th century, laboratories buzzing with new discoveries, scientists exchanging letters filled with excitement and confusion. Einstein was redefining gravity, Rutherford was probing the nucleus, and young minds across Europe were awakening to the strange beauty of the quantum realm. Amid this intellectual storm, Bohr's calm, thoughtful voice stood out. He did not seek dominance or fame, he sought understanding. When asked how he could remain serene while facing such uncertainty, he smiled and said, "Every sentence I utter must be understood not as an affirmation, but as a question." In his private life, Bohr remained grounded and humble. He married Margrethe Enway Relund in 1912, and together they built a home filled with warmth and conversation. Margrethe became his confidant, his translator of thoughts, and often the first listener to his ideas. Evenings in the Bohr household were alive with talk of philosophy, science, and the future. Visitors later recalled that Bohr's home felt like an extension of his mind, welcoming, curious, and endlessly questioning. He believed that collaboration and open dialogue were the lifeblood of science, a belief that would later attract young physicists from around the world to his institute. Still, behind his gentle demeanor, the fire of curiosity burned. Bohr never lost the wonder that had animated his childhood, the sense that the world was both knowable and mysterious. When he lectured, his words carried the rhythm of thought itself, slow and searching, as if he were discovering the truth alongside his audience. Students described how he would pause mid-sentence, close his eyes, and then continue with a phrase that reframed the entire question. To hear Bohr speak was to witness the process of thinking made visible. The world around him was changing fast. The First World War loomed, and the optimism of science began to darken under the shadow of conflict. Yet even in those turbulent times, Bohr's work continued to inspire. His atomic model became a beacon of human creativity, a reminder that even amid chaos, the mind could reach into the heart of the universe and bring back understanding. As soldiers marched and empires crumbled, physicists studied the quiet elegance of Bohr's equations, finding in them a glimpse of order amid disorder. Cinematically, one could imagine the montage newspapers printing headlines about war while, in quiet rooms, scientists trace spectral lines, their eyes reflecting the glow of instruments. The contrast is striking, the noise of destruction outside and the silence of discovery within. Over this imagery, a narrator's voice might echo Bohr's own belief that knowledge is humanity's most powerful form of peace. When the war finally ended, Bohr returned to Denmark with renewed purpose. The scientific world looked to him as a leader of the new quantum generation. His curiosity, once personal and private, now became a guiding force for others. He welcomed young physicists such as Werner Heisenberg, Wolfgang Pauli, and later, many more who would shape the future of quantum mechanics. Together, They transformed the Bohr Institute into a temple of thought, a place where uncertainty was not feared but celebrated. Discussions there often lasted late into the night, filled with laughter, argument, and revelation. Bohr encouraged openness and humility, reminding everyone that the opposite of a profound truth may well be another profound truth. Through all these years, Bohr's fascination with the nature of matter never waned. He saw in the atom a reflection of human existence itself, a delicate balance between chaos and harmony, freedom and constraint. The quantum leaps of electrons, the sudden transitions between energy states, seemed to him almost poetic, symbols of change and possibility. He often said that physics was not about finding the ultimate answer, but about expanding the boundaries of what could be asked. That belief kept his mind alive until his final days. If the film of his life were to linger on one image, it might be that of Bohr standing by the window of his institute, watching snow fall over Copenhagen. The city lights shimmer softly on the icy streets below, and his reflection merges with the darkness outside. In that quiet moment, he seems to be listening again, to the same silent whisper that guided him as a boy, the call of curiosity. The music swells gently, and the narrator's voice fades in, speaking words that Bohr himself might have said, that the universe is not merely to be observed, but to be understood with wonder. His early life, from the curious child surrounded by his father's instruments to the young man who dared to question the foundations of physics, was a journey of awakening. Every challenge, every doubt, every failure had shaped the lens through which he viewed reality. By the time he unveiled his model of the atom, he had already undergone his own transformation, a quantum leap of the mind. Through him, humanity learned that certainty is an illusion, and that the truest knowledge lies in embracing the unknown. As the documentary's final notes fade, the screen might show the faint outline of the hydrogen spectrum, its colored lines gleaming like threads of light across darkness. Then, slowly, Bohr's face appears, calm, thoughtful, illuminated by the glow of understanding. His voice, soft and deliberate, speaks one last time. Everything we call real is made of things that cannot be regarded as real. The words hang in the air, echoing through time, a reminder that curiosity is the bridge between mystery and meaning. The camera pulls back, revealing the vast expanse of the cosmos, stars shimmering, galaxies turning, atoms vibrating with silent rhythm. Somewhere within that cosmic dance lies the same question that once stirred in the heart of a boy from Copenhagen's. What is the nature of reality? And though Bohr's life gave us many answers, his greatest gift was the courage to keep asking. For in every atom, in every flicker of light, in every leap of understanding, the spirit of Niels Bohr endures, the man who looked into the invisible depths of matter and found not only the structure of the atom, but the poetry of existence itself. The year was 1913. The world stood unknowingly at the dawn of a scientific revolution. Steam engines still roared across continents, telegraphs pulsed with the rhythm of progress, and the glow of electric lamps filled the streets of Europe with a newfound brilliance. Humanity believed it understood the rules of nature, the invisible equations that bound energy, matter, and motion together. Yet, beneath this surface of confidence, the atom, the very heart of all things, remained an unsolved riddle. Its structure was a mystery wrapped in speculation, its behavior a contradiction to everything physicists believed they knew. And it was in this uncertain space that a quiet young Dane named Niels Bohr would reshape reality itself. Bohr arrived in Manchester to work under Ernest Rutherford, whose discovery of the atomic nucleus had overturned the established models of matter. Rutherford's atom was a miniature solar system, electrons orbiting a dense central core, much like planets circling the sun. It was elegant, visual, and logical, but it was also deeply flawed. According to Maxwell's laws of electromagnetism, an electron in motion should radiate energy. That energy loss would cause the electron to spiral inward until it collapsed into the nucleus, destroying the atom in a fraction of a second. Yet atoms clearly existed, stable and enduring, forming the fabric of the universe. The model could not be right, not as it stood. Bohr sensed that somewhere in that failure lay the key to something profound. In those early months of 1913, Bohr was immersed in equations and speculation. The laboratory air was heavy with the metallic scent of machinery and the faint trace of chemical reagents. Experiments surrounded him, yet his mind was elsewhere, in the invisible world of particles and forces. He believed that to truly understand the atom, one had to go beyond observation and imagine its inner life. Night after night, he filled notebooks with calculations, the rhythmic scratching of his pen breaking the silence of the laboratory. Each line was a step into the unknown. Bohr had already absorbed the radical ideas of Max Planck and Albert Einstein, that energy does not flow continuously, but in discrete packets called quanta. Planck had discovered this principle while studying blackbody radiation. Einstein had extended it to light itself, explaining the photoelectric effect. Bohr began to wonder, what if this quantum principle applied not only to energy but to matter? What if electrons could exist only in certain allowed orbits, each associated with a specific energy level, and could jump between them by absorbing or emitting a quantum of energy? The thought was daring, a violation of classical mechanics, a rebellion against centuries of deterministic physics. But Bohr was not afraid of contradiction. He believed that truth often hid within paradox. His intuition told him that nature was not smooth and continuous but composed of leaps, invisible transitions that defied human logic. With this conviction, he began to rebuild the atom from the ground up. Imagine the camera zooming in on Bohr's study in Manchester. The flicker of a candle, papers scattered across the table, ink stains marking moments of frustration and insight. His equations began to take form. The radius of an electron's orbit, he proposed, depended on an integer, a whole number representing the quantum number. Only orbits corresponding to these specific values were allowed. When an electron jumped from a higher orbit to a lower one, it emitted a photon of light with energy equal to the difference between those levels, and that energy matched the spectral lines observed in hydrogen's light. A mystery that had baffled scientists for decades. The moment of realization must have felt like electricity coursing through his mind. Hydrogen, the simplest of all atoms, had revealed its secret through mathematics. Bohr's model didn't just explain the mysterious lines in hydrogen's spectrum, it predicted them. The wavelengths of light emitted matched his theoretical calculations perfectly. It was as if nature itself had answered him, whispering, "Yes, you understand." In that instant, a new world of physics opened before him. The atom was no longer a miniature mechanical system, it was a quantum system, governed by strange rules of energy and probability. Bohr's model was both radical and elegant, a bridge between the tangible world of Newton and the abstract world of Planck. It preserved the order of orbits but filled them with quantum meaning. For the first time, the atom made sense. When Bohr shared his results with Rutherford, the older physicist was stunned. The explanation seemed impossible. Electrons jumping between orbits, energy appearing and disappearing in quantity. Yet the numbers worked. Rutherford, though skeptical, recognized genius when he saw it. "You may be right," he told Bohr, with a faint smile that concealed both admiration and disbelief. It was a moment when one era of science quietly handed the torch to the next. Bohr published his theory in a trilogy of papers in Philosophical magazine in 1913 under the title On the Constitution of Atoms and Molecules. These papers became the cornerstone of modern atomic physics. They didn't just describe the atom, they redefined what understanding meant in science. The Bohr model introduced quantization into the heart of matter, a concept that would later evolve into the full quantum mechanics of Heisenberg and Schrödinger. The reception was explosive. Across Europe, physicists read Bohr's papers with a mix of awe and disbelief. Some hailed it as a triumph of imagination, others dismissed it as a fantasy built on fragile mathematics. But no one could ignore the results. The spectral lines of hydrogen, once a chaotic blur of color and confusion, now stood as proof of quantized orbits, glowing evidence of the atom's inner harmony. If one imagines this part of history as film, the scenes would shift between laboratories and lecture halls, scientists studying Bohr's equations projected onto chalkboards, voices murmuring in disbelief, Einstein himself reading Bohr's papers with a wry smile of respect. Over the montage, the narrator's voice might say, "In a world that believed all motion was continuous, Bohr taught us that nature moves by leaps." What made Bohr's model revolutionary was not just its accuracy, but its philosophy. It demanded that scientists abandon the idea of certainty. It declared that the atom was not a tiny clockwork obeying mechanical laws, but a mysterious system where only specific states of being were allowed. The atom did not gradually shift from one energy to another. It jumped. That single idea would change the course of physics forever. But Bohr himself remained humble. He saw his model not as the final truth, but as a step toward a deeper understanding. He knew it could not explain everything. The orbits, though quantized, still seemed too mechanical, too classical. There were contradictions he could not yet resolve, especially when applied to more complex atoms. But Bohr had opened the door. Others would soon walk through it and build the quantum world he had glimpsed. The visual beauty of the Bohr atom captured the imagination of the world. Artists drew diagrams of concentric rings of electrons, elegant and symmetrical. Teachers used it to explain chemistry, energy, and radiation. Even the public, hearing of this new atomic model, saw in it a kind of cosmic order, a miniature universe contained within a single particle. But Bohr knew the truth was deeper and stranger than any diagram. Every description of nature, he would later say, is only a description of what we can say about nature. The atom, in his eyes, was not an object but an idea, a bridge between what we observe and what we cannot. In those early years, Bohr's work inspired a new generation of scientists. Werner Heisenberg, then a young student in Germany, would later recall reading Bohr's papers as a revelation. The clarity of Bohr's thinking, his courage to challenge established law, and his willingness to embrace uncertainty shaped the minds that would soon form the heart of quantum mechanics. Bohr's model was like the first light breaking through the fog, not yet the full day, but enough to reveal the path forward. The years that followed brought both acclaim and challenge. Bohr was invited to Cambridge and later returned to Copenhagen, where he would establish his own institute. His model became the subject of lectures, experiments, and fierce debates. Some physicists, like Sommerfeld, expanded it to include elliptical orbits, refining the theory to explain more complex atoms. Others sought to test its predictions with precise measurements of spectral lines. And as the evidence grew, so did the realization that Bohr had touched something fundamental, something that went beyond physics into the realm of philosophy. If we pause here and imagine the moment through a cinematic lens, we see Bohr standing at a blackboard, his chalk tracing the elegant simplicity of his atom. Students watch in silent awe as he draws a circle, then another, then a line connecting them, an electron leaping from one orbit to the next, releasing a photon of light. The classroom glows with the reflection of understanding. Outside, snow falls softly over Copenhagen, and in that quiet white world, a new vision of the universe is being born. Bohr's atomic model was not just a scientific achievement, it was a new language for reality. It showed that nature was built not on continuity but on discreteness, not on determinism but on possibility. It hinted that at the heart of matter, there was rhythm and harmony, that even chaos followed patterns beyond our intuition. His theory turned the atom into a stage where energy danced in precise steps, each movement accompanied by the music of light. Yet, for Bohr, the most important lesson was not the triumph of prediction, but the humility it demanded. He understood that his model was incomplete, a temporary map of an unexplored world. The quantum domain, he realized, was deeper and more mysterious than anyone could yet grasp, but he had taken the first step, and that step changed everything. By the end of 1913, the name Niels Bohr was known across the scientific world, but in his heart, He remained the same quiet thinker who once watched light through glass as a boy. For him, the atom was not a conquest but a conversation, a dialogue between the human mind and the mysteries of existence. He had not unlocked all its secrets, but he had found a key, and through that key, the door to quantum reality had opened just enough for light to enter. The months following Bohr's publication were like the quiet after a storm. Except the storm was only just beginning. In universities from Cambridge to Göttingen, from Paris to Copenhagen, his model sparked conversations that drifted through hallways and echoed in lecture rooms. To some it was madness, to others revelation. Yet no one could escape the feeling that science had shifted. Something had cracked open in the understanding of matter itself. As Bohr settled back into Copenhagen, letters began to pour in, questions, challenges, praises. He replied to each with patience and humility, for he was never a man of grand claims. He spoke softly, always thoughtful, as though each word needed to pass through the careful sieve of reason before being spoken. He knew that the model he had built was a bridge, not a fortress. It stood strong, but beyond it lay a river of mystery that still had to be crossed. The heart of Bohr's success was its daring simplicity. By limiting electrons to fixed energy states, he had turned chaos into order. But as scientists pushed further, they found that hydrogen alone fit perfectly. Heavier atoms told a more complicated story. The orbits multiplied, interactions tangled, and equations began to strain under the weight of new discoveries. Bohr saw this not as failure, but as evolution. Every great truth, he would say later, is a truth so strong that its opposite is also a great truth. The glow of the Bohr atom illuminated both knowledge and ignorance. It gave scientists a language to describe the invisible, but it also exposed how little they truly understood. And as the decade advanced, a new generation began to rise. Students who had grown up under Bohr's influence, ready to take his ideas further into the unknown. Among them was Werner Heisenberg, a young man of sharp intellect and restless energy, whose meeting with Bohr in the early 1920s would mark one of the turning points in the story of quantum mechanics. Imagine the scene: Copenhagen. The city is quiet under a gray northern sky. Inside the newly established Institute for Theoretical Physics, Bohr and Heisenberg sit surrounded by chalkboards filled with symbols and equations that look like hieroglyphs to the untrained eye. They talk for hours, pacing the room, drawing lines in the air, erasing and redrawing on the board, arguing and laughing in equal measure. What began as Bohr's vision of quantized orbits is now being transformed into something far more abstract. The idea that particles might not even have definite paths at all. Heisenberg, inspired by Bohr's openness to paradox, develops his matrix mechanics, a mathematical framework that abandons the image of the orbit altogether. Schrödinger, working independently in Zurich, creates wave mechanics, where the electron is no longer a particle circling the nucleus, but a cloud of probability, a standing wave of possibility. Both owe their roots to Bohr's atom, yet both go beyond it. The orbit has dissolved, the structure replaced by pure mathematics, yet the spirit of Bohr's idea, the quantization of energy, remains the heartbeat of it all. In documentary imagery, one might see chalk dust floating in sunlight, equations half erased on the board, and Bohr watching Heisenberg with a faint, knowing smile. He recognizes in the young physicist's struggle the same storm of thought he once endured in Manchester. Bohr's model is being dismantled, but it is not dying. It is evolving, just as he always hoped it would. By the mid-1920s, quantum mechanics has taken form, and Bohr stands at its philosophical center. His atomic model, though simplified, becomes a teaching tool, a stepping stone for every new student entering the strange world of quanta. But Bohr's true contribution now moves beyond physics into the realm of interpretation. How can one speak about a world that defies all intuition? What does it mean to say that an electron exists here or there, if we can never observe it directly? These were not questions of numbers but of meaning, and Bohr was determined to answer them. He introduced what would become known as the principle of complementarity, the idea that light and matter can behave both as particles and waves, but never both at the same time. The nature of reality, Bohr proposed, depends on how we choose to observe it. In one experiment, we see a particle, in another, we see a wave. Both descriptions are true, yet mutually exclusive. This was not contradiction, it was completeness. The universe, he suggested, could only be understood through the coexistence of opposites. Such ideas startled even his closest colleagues. Einstein, who admired Bohr deeply, resisted the notion that chance and observation defined reality. God does not play dice, Einstein famously declared, to which Bohr calmly replied, Einstein, stop telling God what to do. Their debates became legendary, two giants standing on the frontier of human knowledge, arguing over the nature of existence itself. And behind their words, the quiet pulse of the Bohr atom still beat steadily, reminding them of how far they had come from that simple image of electrons circling a nucleus. If one were to narrate this chapter like a film, the scene might cut between Einstein's furrowed brow, Bohr's patient half-smile, and a glowing image of an atom projected on a wall, its electrons flickering in quantum uncertainty. The music would rise, a mix of curiosity and wonder, as the narrator's voice intones, from a model of orbits came a model of existence. Bohr's Institute became a haven for young physicists from every corner of the world. They came not just to study but to think. The building itself was modest, simple rooms, wooden floors, and walls lined with blackboards. But within those walls, the future of physics was being written. Heisenberg, Pauli Dirac, and many others passed through its doors. In that community of minds, guided by Bohr's patience and vision, the quantum revolution matured. Yet even as the theory grew more precise, its strangeness deepened. Experiments confirmed predictions that seemed to defy logic, particles behaving as if they knew they were being observed, probabilities interfering like waves, reality flickering between possibilities until measured. Each result was another echo of Bohr's insight. Nature does not reveal itself directly, it only answers the questions we are capable of asking. By the 1930s, the Bohr atom had become both a symbol and a teaching tool, printed in textbooks, drawn on classroom walls, and adopted as the universal image of science itself. Those concentric rings, though no longer literal, captured the imagination of the public. The atom had become the icon of the modern age, a miniature cosmos representing both the order and mystery of creation. And behind that symbol stood Bohr, modest, reflective, often smiling shyly when praised. He never claimed ownership of the revolution he began. The task of science, he would say, is not to find out what nature is, but what we can say about nature. Then came the war. As the world descended into conflict, the quantum pioneers were drawn into a new and terrifying chapter. The understanding of the atom that began with curiosity now held the power to destroy cities. Bohr, deeply troubled, found himself entangled in the race for atomic knowledge. His insights into nuclear fission helped guide research, but his heart was heavy with the moral burden it carried. When the first atomic bombs were built, Bohr's thoughts were not of triumph but of fear. He urged the world to treat atomic energy not as a weapon, but as a responsibility. In documentary imagery, this period would be filmed in muted tones, Bohr walking slowly through his garden in Copenhagen, his face lined with worry, newspapers on his desk carrying headlines of destruction. The narrator's voice softens. The man who unlocked the atom dreamed not of power, but of peace. After the war, Bohr became a global advocate for scientific openness. He believed that knowledge should unite humanity, not divide it. His Open World letter to the United Nations called for transparency and cooperation in nuclear research. It was a message born from the same humility that shaped his science, that understanding demands honesty, and that no single person or nation owns the truth. Yet through all these decades, the core of his genius remained unchanged. The vision of the atom as a quantum system, a dance of probabilities and energies. Though modern quantum mechanics had far surpassed his 1913 model, every new discovery traced its lineage back to those early papers. Those long nights of thought when Bohr dared to imagine that electrons did not spiral into the nucleus, but leapt between invisible states like notes in a cosmic melody. In the twilight of his life, Bohr often revisited that melody. He loved to walk through the gardens near his home, watching sunlight filter through leaves, the patterns of light and shadow playing like waves across the ground. To him, these simple sights carried the same wonder as the atom itself. Nature, he would say, is subtle beyond imagination, and every answer reveals another question. He lived to see his ideas validated countless times over, through spectroscopy, through quantum chemistry, through the technologies that shaped the modern world. The computers, lasers, and semiconductors of today all owe a debt to the quantum principles that began with his model. The universe itself, from stars to DNA, is now understood through the lens of quantization that Bohr first placed upon the atom. And yet, if we could step back in time to that small room in Manchester, to that moment when he first wrote down his equations, we might realize that Bohr's greatest discovery was not just the atom's structure, but the nature of human curiosity. His model represented the courage to imagine what cannot be seen, to question what seems obvious, to accept that truth may exist in forms that defy common sense. In the closing moments of such a film, we would see Bohr at his desk, older now, surrounded by photographs of his students, his papers carefully stacked. Outside, the evening sun glows red over Copenhagen. He sets down his pen, gazes at the horizon, and perhaps whispers to himself that the quest to understand the universe is never finished. Then, softly, the narrator's voice concludes, "In 1913, a young physicist looked into the heart of the atom and found not certainty, but wonder. From that wonder came the language of the quantum world, a language that speaks of light, of probability, and of the delicate balance between what is known and what can never be known." Niels Bohr did not just unlock the atom. He revealed that the smallest parts of nature hold the deepest questions of existence itself. And the screen fades to black, leaving only the quiet pulse of light, a single glowing atom, orbiting in endless possibility. The story of Niels Bohr did not end with his atomic model. In many ways, it only began there. The model had revealed the structure of the atom, but not the nature of the universe that contained it. The success of quantum theory had raised deeper, stranger questions, questions about what reality itself might mean. If electrons could exist in multiple states until observed, if light could behave both as a wave and a particle, then what was truth? What was existence? And could science, which had always promised certainty, still deliver it? These were not questions of mathematics alone. They were questions that touched philosophy, logic, even the meaning of perception itself. Bohr, more than any other physicist of his age, was willing to face them. By the mid-1920s, quantum mechanics had become a storm of brilliance and confusion. Heisenberg's matrix mechanics and Schrödinger's wave equation were both astonishingly successful. Each could describe the motion of electrons and predict the outcomes of experiments with incredible accuracy. Yet, they seemed to describe entirely different worlds. Heisenberg's mathematics had no clear picture, no orbits or waves, only arrays of numbers that obeyed strange new rules. Schrödinger's wave function, on the other hand, described particles as continuous ripples of possibility. Both worked, both were right, and yet they could not both be true in the same way. The paradox was intolerable. Science demanded unity, and it was Bohr who would find the bridge. He watched these developments with calm fascination from his institute in Copenhagen, where the greatest minds of physics gathered in restless debate. Bohr was not the loudest voice, nor the quickest to answer. He listened, his eyes distant and thoughtful, as if weighing every word against some invisible truth. To him, the contradictions were not signs of failure, but clues. Perhaps nature itself was built on contradiction, not as chaos but as balance. Perhaps the universe was not one story, but two, told from different points of view, each incomplete without the other. In 1927, Bohr crystallized this insight into a single principle. A principle so subtle and profound that it would redefine the philosophy of science. He called it complementarity. The idea was that the wave and the particle, though seemingly opposed, were not enemies but partners. They were complementary aspects of one deeper reality, two faces of the same truth, each revealed only under specific conditions. To observe one was to hide the other, not because of any flaw in measurement, but because of the way nature itself was built. Imagine the double-slit experiment, that hauntingly simple test that had puzzled scientists since Thomas Young first performed it a century earlier. When light passes through two narrow slits, it produces an interference pattern on the screen, a ripple of bright and dark bands that reveals its wave-like nature. But if you place detectors to see which slit each photon passes through, the pattern vanishes. The light behaves like discrete particles instead. The mere act of measurement changes the outcome. It was as if the universe refused to show both faces at once. To Bohr, this was not an anomaly, it was a message. The complementarity principle said that what we observe depends on how we observe it. Reality, in the quantum world, cannot be described without reference to the act of observation itself. The observer and the observed are intertwined. It was an idea so revolutionary that it shook the very foundation of objectivity. The old dream of a detached scientist, watching nature unfold from a distance, was gone. In the quantum world, participation was unavoidable. Every measurement, every question, every act of looking shaped what could be known. The documentary lens might show Bohr explaining this to his students in a quiet lecture room, his hands drawing invisible waves in the air. "We are not only spectators," he would say softly. "We are participants in the drama of existence." His words were not poetry, they were the new physics. And behind his calm voice lay a deep humility, the sense that humanity had reached the edge of what could be known in the traditional sense. The quantum world was not hidden because of ignorance, it was hidden by its very nature. Bohr's principle was tested not just in laboratories but in minds. Einstein, ever the realist, could not accept it. To him, nature must have definite properties whether or not they were observed. "The moon," he said, "surely exists even when no one is looking at it." Bohr agreed, in a sense, but insisted that physics could not describe that kind of reality. Physics, he argued, could only describe the results of experiments, the knowledge we gain, not the unknowable things in themselves. It was not a retreat from truth, but an acceptance of its limits. Einstein called it surrender. Bohr called it honesty. Their debates became legendary. The great dialogues of the Solvay conferences in Brussels, where the giants of physics gathered in smoke-filled rooms, their arguments echoing through history. Einstein would present paradoxes designed to expose the weakness of quantum theory, thought experiments involving clocks, boxes of photons, or particles entangled across vast distances. Bohr, patient and unflappable, would listen, pause, and then respond with insights so deep they seemed almost mystical. He always found a way to show that quantum mechanics remained intact, that complementarity could survive every test. In one such moment, Einstein proposed that by weighing a box before and after releasing a photon, one could determine both its energy and the exact time it left, violating Heisenberg's uncertainty principle. Bohr, disturbed but composed, spent a sleepless night thinking. The next morning, he returned with an answer that stunned the room. Einstein's thought experiment failed because gravity itself, through general relativity, would alter the measurement of time. The very act of weighing the box would shift the clock's rate, preserving uncertainty after all. Einstein could only smile and nod, impressed. Bohr had used Einstein's own theory against him. These exchanges were more than intellectual duels, they were the living heartbeat of 20th century science. Through them, Bohr refined his philosophy, shaping not just quantum physics, but the way scientists would think about knowledge itself. To him, complementarity was not limited to light and matter. It was a universal principle, a way of understanding opposites. The mind and the world, the subject and the object, the known and the unknown, all were complementary aspects of a deeper wholeness. In a documentary scene, the camera might linger on Bohr walking alone along a misty Copenhagen shoreline, his coat fluttering in the wind. The gray sea stretches before him, calm yet infinite. The narration might say, he sought not the certainty of answers, but the harmony of opposites. It was this harmony that became the guiding light of his later life. Complementarity soon became more than a scientific idea, it became a philosophy of existence. Bohr saw it reflected everywhere: in psychology, where conscious and unconscious minds shape one another; in art, where abstraction and form coexist; in ethics, where freedom and responsibility define each other. For Bohr, nature and human thought were bound by the same logic of duality. The truth could not be captured in isolation. It emerged only through interaction. Even his famous coat of arms bore the yin-yang symbol, with the motto Contraria sunt complementa, opposites are complementary. It was both a statement of physics and a reflection of his worldview. To Bohr, the quantum world was not chaos but balance, a balance so delicate that it demanded humility from all who sought to grasp it. Meanwhile, experiments continued to confirm his insights. The uncertainty principle, proposed by Heisenberg under Bohr's mentorship, became the mathematical companion to complementarity. It stated that one could never know both the position and momentum of a particle with infinite precision. The more one is known, the less certain the other becomes. This was not a flaw of instruments, it was a feature of reality. Bohr's complementarity gave it meaning. The wave picture reveals one kind of truth, the particle another, but neither alone can describe the whole. Through the late 1920s and 1930s, Bohr became the philosophical center of the quantum community. His institute, once a gathering place for dreamers, had become the cradle of modern physics. Visitors described an atmosphere unlike any other, intense yet gentle, full of debate, yet united by respect. Bohr himself guided discussions with quiet authority, often answering a question with another question, forcing his students to think, to see from multiple perspectives. He was not a teacher who dictated knowledge, he was one who helped others find it within themselves. Imagine a quiet evening at the Institute, the lamps glowing softly, papers scattered across tables, chalkboards filled with symbols that shimmer faintly under the light. Bohr sits at the head of the table, listening as Heisenberg and Pauli argue over an equation. When the debate grows heated, he raises a hand and smiles. "You are both right," he says. "You are simply describing the same thing from different sides." That was Bohr, never the conqueror of truth, but its patient interpreter. The world around him, however, was changing. Beyond the walls of his institute, political tensions were rising, and science itself was becoming entangled with power. Yet Bohr held firmly to his belief that knowledge must remain open, collaborative, and shared across borders. His philosophy of complementarity extended even to human affairs. Only through dialogue, he believed, could conflicting perspectives find harmony. By the early 1930s, Bohr's ideas had become foundational. Complementarity was accepted not only as a way to interpret quantum mechanics, but as a principle of thought itself. Even Einstein, though unconvinced, respected Bohr's depth and sincerity. Their debates, he admitted, had taught him much. It was perhaps the highest praise one thinker could give another. In those years, Bohr's face began to appear in newspapers and scientific journals. He was portrayed as a philosopher of science, a man who bridged the gap between physics and meaning. Yet to his colleagues, he remained the same humble figure, gentle and self-effacing, always giving credit to others. "Physics," he often said, "is not about finding out how nature is, but about finding out what we can say about nature." To the untrained ear, this might sound evasive, but to Bohr, it was the essence of scientific truth, that reality is richer than language, and that every description is a kind of translation, limited by perspective. The quantum world was not a hidden clockwork waiting to be revealed, it was a conversation between nature and observer, where each answer depended on the question asked. As Parta closes, imagine the final image, Bohr standing before a large blackboard covered in equations, the chalk dust rising like mist. He turns, smiles faintly, and says, "In the end, the universe does not ask to be understood. It only asks to be observed, with honesty, with humility, and with wonder." The music swells, quiet, reflective, and the screen fades to darkness. The sun was setting over Copenhagen, its light melting across the calm surface of the harbor, and inside Niels Bohr's institute the lamps were beginning to glow. On most evenings, when the last of the students had gone home and the city's sound softened into silence, Bohr remained at his desk. Sometimes he would walk slowly through the corridors, his hands clasped behind his back, the echoes of his footsteps mingling with the faint hum of distant conversation. Those who saw him at these hours said it was as if he were listening, not to people, but to the universe itself. In those long, quiet walks, the idea of complementarity matured from a scientific insight into a philosophy of existence. The mid-1930s were an age of paradox, a world of discoveries shadowed by fear. Quantum mechanics had transformed the understanding of matter, yet it had also created unease. The certainty of Newton's universe had vanished. In its place was a world of probabilities, where cause and effect danced in unpredictable patterns. Many physicists found this deeply unsettling. Einstein still argued that something must be missing, that hidden variables might restore order. Bohr, however, saw beauty in the ambiguity. For him, uncertainty was not ignorance, it was the signature of nature's complexity. He often compared the quantum world to art or music, domains where contradiction becomes harmony. In a symphony, dissonance resolves into melody. In painting, contrast brings depth. So too, he said, in physics opposites complete one another. His lectures were not like those of other scientists, filled with equations and proofs. They were journeys of thought. Students recalled how he would pause mid-sentence, searching for the right word, then smile softly and say, "Perhaps the problem is not in nature, but in our language." He believed that words, like measurements, shape the world they describe. The essence of complementarity was beginning to echo far beyond physics. Psychologists, philosophers, and even theologians began to find resonance in Bohr's vision, the idea that truth might require multiple, even contradictory, descriptions to be complete. Jung saw parallels between Bohr's dualities and the balance of the conscious and unconscious mind. Artists found in his theory a validation of modern abstraction, that form and emptiness, color and silence, could coexist. The boundaries of science were dissolving into a larger human understanding. In the scientific community, however, the debates raged on. Einstein, Podolsky, and Rosen published their famous paper in 1935, presenting what they believed was a fatal challenge to Bohr's interpretation. They described a pair of particles that, once interacted, would remain linked, so that measuring one instantly determined the state of the other, no matter how far apart they were. This spooky action at a distance, as Einstein called it, seemed to suggest that quantum mechanics was incomplete. If observation of one particle affected another instantaneously, then either information traveled faster than light, or something hidden and unaccounted for existed beneath the surface. When Bohr read the paper, he sat in silence for a long time. Those who were present said he read it again and again, his brow furrowed not with anger, but with deep thought. Then he looked up and said almost softly, "Einstein is right, in a way, but not as he believes." Over the next days, Bohr composed his response, a masterpiece of philosophical precision. He argued that the paradox was not a failure of quantum theory, but a misunderstanding of what measurement meant. The properties of a system, he explained, do not exist independently of the experimental setup. Once two particles become entangled, they are not separate objects but parts of one system. To measure one is not to disturb the other from afar, it is to define the whole. The apparent spooky connection was not transmission but relationship, a subtle, invisible unity binding the universe together. This was Bohr at his most profound. He was no longer merely describing electrons or photons, he was describing the very architecture of reality. In his view, separateness itself was an illusion. Nature was holistic, woven from threads that could not be torn apart without changing the pattern. The documentary camera might now move through a starry night, the voice of the narrator quiet and meditative. To Bohr, every observation was a dialogue between the part and the whole, a reminder that the universe speaks only when we learn to listen. As war began to engulf Europe, Bohr's work took on new urgency and new meaning. Many of his students and colleagues were forced to flee. Some sought refuge in his home, where he hid them under the pretext of scientific collaboration. The Nazis invaded Denmark in 1940, and Bohr found himself caught between duty to his country and loyalty to humanity. When word came that he would be arrested, he escaped by fishing boat across the Øresund to Sweden, then flew in a small military plane to Britain and eventually to America. Even in exile, he carried his philosophy with him, the belief that understanding must be shared, that secrecy was the enemy of progress. In America, he was drawn into the Manhattan Project, the effort to build the atomic bomb. It was a bitter irony. The man who had unlocked the atom now helping to unleash its power. Yet Bohr's role was never that of an engineer of destruction. He was a conscience, a moral compass. He urged openness among the Allies and foresight about the world that would follow. "We are in a race between cooperation and catastrophe," he said. His principle of complementarity now took on a human dimension, the need to reconcile security and freedom, science and ethics, power and responsibility. When the war ended, Bohr returned to Copenhagen and resumed his life as both scientist and philosopher. The institute was rebuilt, and once again it became a beacon for young minds from around the world. They came not just to learn quantum theory, but to absorb Bohr's way of thinking, his patience, his humility, his faith in dialogue. Even decades after the publication of his 1913 papers, his office remained a kind of pilgrimage site, its walls lined with photographs, books, and the quiet hum of ideas. Visitors noticed that his desk was always cluttered with letters from across the globe, scholars, poets, and politicians all seeking his wisdom. It was during these years that Bohr's principle began to mature into something broader, almost universal. He saw complementarity not as confined to physics, but as a fundamental pattern of reality, the tension between opposites that generates meaning. In nature, particle and wave; in life, action and reflection; in society, individual and community. He often spoke of the need to embrace both sides, to resist the temptation of absolutes, the opposite of a profound truth. He would say with a gentle smile, "May well be another profound truth." To his students, this was more than a motto, it was a way of seeing the world. Bohr's conversations could move effortlessly from quantum theory to poetry, from mathematics to ethics. He believed that understanding required imagination, that logic alone could never capture the fullness of experience. One afternoon, while discussing atomic structure, he paused and pointed to a painting hanging in his office, an abstract swirl of color and light. "You see," he said, "the artist and the physicist seek the same thing, to make the invisible visible." Outside the world was entering a new age of science. Nuclear energy, computers, and radio waves, all were children of the quantum revolution. Yet Bohr remained deeply aware of the moral questions that came with such power. He became an advocate for global cooperation in nuclear research, meeting leaders and writing letters to governments urging transparency. His proposal for an open world, presented to the United Nations in 1950, called for an end to secrecy and the free exchange of scientific knowledge. "The survival of civilization," he wrote, "depends on our ability to combine technical knowledge with human wisdom." It was complementarity on a global scale. Even in his later years, Bohr continued to explore the philosophical implications of his principle. He saw it reflected in biology, where life balances structure and change; in psychology, where thought and emotion intertwine; even in language, where meaning emerges from the tension between word and context. The idea had grown from a solution to a physical paradox into a universal metaphor, a reminder that truth is rarely one-sided. The documentary would now slow its pace, Focusing on Bohr's aging face, his eyes still bright behind round glasses, he speaks softly to a group of young students gathered in his office. The war is over, the world rebuilt, but his message remains urgent. Every generation, he says, must learn that knowledge is only half of wisdom. The other half is understanding the limits of knowledge. Outside, the bells of Copenhagen ring through the evening air. As the 1950s gave way to the 1960s, Bohr's health began to fade, but his influence only deepened. Experiments around the world confirmed the strange predictions of quantum theory: entanglement, superposition, uncertainty, all resonating with his philosophy. The ideas that once seemed mystical now became the foundation of technology. The transistor, the laser, and the emerging computer age were all children of the quantum world. Bohr's principle had not only survived, it had become the hidden architecture of the modern age. Yet he never sought fame. When journalists visited, hoping for bold statements or sweeping predictions, he would smile politely and redirect the conversation. "It is not the future that matters," he would say, "but our attitude toward it." Those who worked with him remembered his gentleness, his pauses, his way of turning a question into reflection. He rarely gave direct answers. Instead, he opened doors in the listener's mind. In one of his last recorded interviews, Bohr was asked whether he believed the human mind would ever fully understand the universe. He leaned back, thought for a moment, and replied, "I think the universe is simple, but we are not simple enough to see it." It was a line that carried both humor and humility, the perfect expression of complementarity itself, knowledge and mystery coexisting in a single breath. On November 18, 1962, Niels Bohr passed away at his home in Copenhagen. The news spread quietly across the scientific world, and tributes poured in from every continent. To many, his death marked the end of an era, the passing of the last of the great founders of quantum mechanics. Yet to those who understood his message, it was not an ending but a continuation. His ideas had become part of the world's intellectual DNA. Every equation written in quantum physics, every debate about the nature of reality, carries the echo of his thought. If we imagine the final moments of this documentary, the camera might move through the rooms of his institute. The empty chalkboards, the scattered papers, the light filtering through the windows. The narrator's voice, calm and reflective, would say, "He taught us that nature does not reveal itself through certainty but through relationship. That truth is not a single note but a chord. That knowledge without humility is blind, and observation without imagination is empty." Through complementarity, Niels Bohr gave the world not only a new physics but a new way to see itself. The music would swell softly, a blend of strings and quiet piano. The scene would shift from the laboratory to the cosmos. Atoms spinning, galaxies swirling, the same patterns repeating across scales. Then, in a final image, a beam of light passes through two slits, forming its delicate interference pattern on the screen. As the camera draws close, the pattern dissolves into the face of Bohr himself, smiling faintly, as if amused by the eternal mystery he helped uncover. The voice concludes, "In every experiment, in every thought, the universe reminds us opposites are not enemies, but partners." And somewhere, between wave and particle, between knowing and wondering, lies the quiet genius of Niels Bohr. The screen fades to black, leaving only a pulse of light, a single photon, flickering, alive, the smallest whisper of complementarity. The world of science stood at the crossroads of mystery and revelation when Niels Bohr began to reshape the laws of nature. His atomic model had already brought light to the invisible dance of electrons, but its implications reached much further. The fourth keynote, the transformation of modern physics through Bohr's vision, marked the dawn of a new scientific era, one that would redefine how humanity saw reality itself. It was not merely a theory, it was a revolution of understanding, a shift in the human mind that altered the foundation of truth. In the early 20th century, physics was a fortress of certainty. Newton's mechanics ruled like an ancient kingdom, explaining motion, gravity, and light with near-perfect precision. The universe, it seemed, was a machine built on predictable gears. But Bohr saw cracks in the mechanism, strange, unexplained phenomena that refused to fit within its logic. The behavior of atoms and light seemed to disobey the classical laws, acting as if they were alive, aware, and unwilling to be pinned down by measurement. Bohr did not see this as failure, he saw it as a clue. With quiet determination, he built a new model of the atom that would soon become one of the cornerstones of modern physics. He imagined electrons not as particles moving freely, but as entities bound to specific orbits, each orbit carrying a distinct energy. The transitions between these orbits created light, tiny flashes of energy released or absorbed, explaining the strange patterns scientists had observed in spectral lines. For the first time, the invisible world of the atom began to make sense. Bohr's equations matched reality, and the elegance of his explanation stunned the scientific community. But what made Bohr's transformation so powerful was not only the correctness of his model, it was the philosophy behind it. He challenged the assumption that nature must always behave according to human intuition. The universe, he suggested, is not obligated to be simple or comforting. It is only obligated to be true. In this humility lay the seed of the quantum revolution. Bohr's work became the bridge between classical physics and the new world of quantum mechanics. It connected the precision of mathematics with the unpredictability of nature. When Heisenberg, Schrödinger, and Dirac expanded upon Bohr's ideas, the entire structure of science began to shift. No longer was reality seen as a static set of objects, it became a dynamic field of possibilities. Observers themselves became part of the equation, their act of measurement influencing the outcome. It was a radical notion that altered not only science but philosophy itself. In lecture halls across Europe, young scientists gathered to hear Bohr speak. His voice was calm, his pace deliberate, as though he was thinking aloud, and inviting the audience to think with him. Those who attended said it felt like being drawn into the very fabric of reality. He would pause for long moments, eyes closed, then open them with a sudden flash of insight. The task of science, he once said, is not to find the final truth, but to understand the relationships that make truth possible. This was the essence of his revolution, a call to see knowledge not as conquest, but as conversation. The transformation Bohr initiated spread far beyond physics. It influenced chemistry, biology, and even the philosophy of consciousness. The quantum view he helped to shape revealed that matter itself was not solid, but a field of probabilities. A shimmering, vibrating sea of energy where everything was connected. This was the birth of modern physics, the foundation upon which relativity, quantum mechanics, and particle theory would grow. The discovery of quantum behavior led to the development of technologies that would transform the world. From lasers and transistors to computers and nuclear energy, Bohr had not just changed equations, he had changed civilization. In the quiet of his institute, Bohr often reminded his students that understanding nature was also understanding our limits. Every great discovery, he said, is a recognition of how little we truly know. His humility stood in contrast to the power of his insights. While others sought control over nature, Bohr sought harmony with it. He believed that the mystery of the atom was not something to be conquered, but something to be listened to. A dialogue between the mind and the cosmos. As the years passed, the implications of his work continued to unfold. Einstein's relativity had redefined space and time, but Bohr's quantum theory redefined existence itself. Together, they completed the foundation of modern physics. One describing the cosmic, the other the microscopic. Yet Bohr's influence went deeper than theory. He transformed the way scientists thought, teaching them that truth might wear different faces depending on how we look. His principle of complementarity became a metaphor for all knowledge. That light can be both wave and particle, that reality itself may require multiple perspectives to be seen clearly. The transformation Bohr brought to modern physics was not a single discovery, but an awakening. He taught humanity to look at the universe with wonder, not certainty, with curiosity, not pride. In doing so, he unlocked more than the atom, he unlocked the human imagination. His legacy is written not only in scientific journals but in the silent awe that comes when one realizes that everything, from the stars to the smallest particle, follows laws born from mystery in mind. When Bohr looked at the atom, he did not just see a particle of matter, he saw a symbol of the universe's duality. Simplicity and complexity, chaos and order, logic and wonder. Through his work, modern physics became more than a science, it became a philosophy of existence. And so, in every beam of light, in every quantum leap, there remains the echo of Bohr's voice, calm, reflective, and eternal, reminding us that knowledge is not an end, but a journey through the infinite. In the world of science, certain encounters shape the course of human understanding forever, and few were as profound as Niels Bohr's collaborations with Albert Einstein and Werner Heisenberg. These were not just meetings between scientists, but confrontations between ideas, logic against mystery, certainty against probability, and classical order against quantum chaos. The fifth keynote, Bohr's collaboration and intellectual duels with these two great minds, became one of the most dramatic and enlightening chapters in the history of physics. It was a dialogue that defined an era, a struggle not for victory but for truth. It began with mutual respect. Einstein, the elder genius who had redefined time and space, saw in Bohr a kindred spirit, another seeker of nature's hidden logic. When Bohr first presented his atomic model, Einstein admired its elegance but sensed a deeper tension beneath it. For Einstein, the universe was governed by laws of certainty. Every cause had its effect, every motion a reason. But Bohr's quantum vision defied that simplicity. It suggested that at the heart of reality lay chance, that particles could exist in many states until measured, and that observation itself shaped the outcome. To Einstein, this was unthinkable. He famously declared, "God does not play dice with the universe." Yet Bohr, with his calm and quiet voice, responded, "Einstein, stop telling God what to do." Their debates became legendary, unfolding in lecture halls, conferences, and long evening walks. At the Solvay conferences of the 1920s and 1930s, the world's greatest physicists gathered, and at the center of it all stood Bohr and Einstein, circling one another like philosophers of old. Einstein would present thought experiments designed to expose flaws in quantum theory. Imaginary boxes, mirrors, and slits through which light would behave in impossible ways. Each time, Bohr would listen patiently, sometimes pacing the room, sometimes pausing for hours before answering. And each time, he found a way to defend the strange logic of the quantum world. His counterarguments were not only scientific but poetic, as if he understood that the universe spoke a language deeper than equations. Heisenberg, on the other hand, was not Bohr's opponent but his protégé. The two worked closely in Copenhagen, where Bohr's institute became the cradle of quantum mechanics. It was there that Heisenberg, inspired by Bohr's ideas, developed his uncertainty principle, the notion that one can never simultaneously know both the position and the momentum of a particle with complete precision. The more you know one, the less you know the other. Bohr immediately recognized the philosophical weight of this discovery. He saw in it the perfect expression of complementarity, his belief that reality reveals itself only through the interplay of opposites. Heisenberg's mathematics became Bohr's philosophy, and together they wove the fabric of quantum mechanics. One thread of logic, the other of meaning, their collaboration was not without tension. Heisenberg was bold, mathematical, and sometimes impatient. Bohr was reflective, slow to speak, careful with every word. But this contrast made their partnership powerful. They challenged and refined one another's thoughts, turning uncertainty from a problem into a principle of nature. To watch them at work, as colleagues later recalled, was to witness the very act of creation, a conversation that turned the unknown into understanding. When the shadows of war fell over Europe, their relationship took on a painful dimension. Heisenberg, working in Germany under the Nazi regime, visited Bohr in occupied Denmark in 1941. The meeting remains one of the most mysterious moments in history. No one knows exactly what was said. Some claim Heisenberg sought Bohr's advice. Others believe he was warning him about Germany's nuclear ambitions. Whatever passed between them, it left both men shaken. Bohr, deeply troubled, escaped to Sweden soon after, carrying with him not only scientific secrets, but the heavy burden of moral responsibility. Their friendship, though strained by circumstance, endured in mutual respect until the end. Bohr's interactions with Einstein and Heisenberg were more than personal exchanges. They were the crucible in which modern physics was forged. Einstein forced Bohr to sharpen his ideas, to find meaning in the apparent chaos of quantum phenomena. Heisenberg helped him transform those ideas into a coherent theory that explained the world at its most fundamental level. Together, their debates and collaborations shaped a new language for reality, one that embraced paradox as truth. These relationships revealed Bohr's greatest strength, his ability to see science not as conflict, but as dialogue. He never sought to defeat Einstein or dominate Heisenberg, he sought to understand them. In every disagreement he found insight. In every challenge he found growth. To Bohr, knowledge advanced not through victory, but through conversation, through the meeting of minds that dared to question the universe. In the imagined light of a documentary, we might see Bohr standing before a chalkboard, the air thick with cigarette smoke, his hand tracing orbits and waves as he explains the unexplainable. Across from him, Einstein listens, arms folded, eyes bright with curiosity. In another room, Heisenberg scribbles equations in frustration, then looks up with sudden realization. Their voices, their thoughts, and their silences intertwine like the particles they describe, inseparable, entangled, and forever shaping one another. What emerged from these encounters was not a single truth, but a harmony of opposites. Einstein's quest for certainty met Bohr's embrace of uncertainty. Heisenberg's mathematics met Bohr's philosophy. Together, they revealed that science is not about finding the final answer, but about learning to live with the eternal question. Through these collaborations and debates, Bohr helped transform physics from a study of objects into a study of relationships between light and matter, mind and measurement, theory and reality. And when history looks back, it is not the arguments that are remembered, but the respect. The image that remains is of three minds standing at the edge of knowledge, gazing into the unknown, each seeing a different reflection of truth. Bohr, with his gentle conviction, taught them, and us, that even disagreement can be a form of unity. The world of physics, and perhaps the world itself, owes its deepest wisdom to that timeless conversation between giants. In the quiet corridors of Niels Bohr's Institute in Copenhagen, ideas were born that would forever redefine the meaning of reality. The sixth keynote, his role in shaping the Copenhagen interpretation of quantum mechanics, was not merely a scientific milestone. It was a revolution of thought. It told humanity that the universe was not as straightforward as it seemed, that certainty was an illusion, and that observation itself could shape the nature of existence. It was a theory that challenged centuries of belief and forced humankind to look at the world not as fixed, but as fluid, a place where possibilities danced in the shadows of perception. It began with a question that haunted every physicist of the early 20th century: what truly happens inside the atom? When scientists observed electrons, they found something baffling. Sometimes they behaved like solid particles, and sometimes like waves of energy. When unobserved, they seemed to exist everywhere and nowhere at once, as if reality waited for someone to look before deciding what to become. This was the mystery that Bohr sought to understand. He realized that nature at the quantum level could not be described in absolute terms. It was not that electrons were either particles or waves, but that they could be both, depending on how we chose to observe them. From this insight grew the heart of the Copenhagen interpretation. Bohr proposed that the act of measurement was not passive, it was participatory. The observer and the observed were inseparable. Reality, at its most fundamental level, was not a collection of independent things but an interaction, a conversation between mind and matter. The universe, in this view, did not exist as a definite structure until it was experienced. It was an idea both simple and terrifying that consciousness, in some subtle way, played a role in bringing reality into being. Einstein resisted this notion fiercely. To him, the universe existed whether or not anyone was looking. He believed Bohr's interpretation reduced physics to philosophy. But Bohr was not denying reality, he was redefining it. He argued that quantum mechanics did not describe how things are, but how things appear when we interact with them. The wave function, the mathematical heart of quantum theory, was not a map of what exists but of what could exist. Once observation occurred, the wave collapsed into a single outcome. In Bohr's eyes, this was not magic, it was nature's language of probability. The Copenhagen interpretation became the cornerstone of modern quantum mechanics. It gave scientists a framework to calculate and predict atomic behavior with astonishing accuracy. Experiments confirmed its predictions again and again: the double slit experiment, electron diffraction, and later, the eerie phenomenon of quantum entanglement. Yet even as it succeeded, it left philosophers and physicists alike uneasy. The theory worked perfectly, but what it meant remained elusive. Bohr's interpretation told us that we could never see the quantum world directly, only its shadows on the screen of experience. To seek a deeper reality beyond observation, he said, was to ask a question nature could not answer. Inside his institute, Bohr's discussions with students and colleagues often stretched long into the night. The young physicists who gathered there, Heisenberg, Pauli, Born, and others, debated the meaning of every experiment. They argued, laughed, and sometimes fell silent, overwhelmed by the vastness of what they were uncovering. Bohr, with his slow, thoughtful speech, guided them patiently. He reminded them that the goal of science was not to dictate how the world must be, but to understand how it reveals itself. To those who found the Copenhagen interpretation unsettling, he would smile and say, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." Through Bohr's influence, the Copenhagen interpretation became the philosophical backbone of quantum theory. It shaped how generations of scientists approached the unseen world. It demanded humility, the acknowledgement that our knowledge is always incomplete, that observation itself changes what is observed. In this framework, uncertainty was not failure, but the very essence of truth. Nature, Bohr taught, was not a book written in human language. It was a poem, one that changed its rhythm depending on who was reading. The interpretation also carried deep implications for human thought. If reality depended on observation, then knowledge and existence were intertwined. The line between the observer and the universe began to blur. This notion resonated far beyond physics, inspiring artists, philosophers, and mystics. The world began to see science not as the conquest of mystery, but as a dialogue with it. In the imagined glow of a documentary frame, we might see Bohr standing beside a chalkboard filled with equations, his students gathered around, their faces lit by the soft light of understanding. He moved slowly, gesturing with a piece of chalk, explaining that the atom is not a tiny solar system but a symphony of probabilities, a place where potential and reality meet. His words are calm, deliberate, yet they carry the weight of an idea that will change everything. The Copenhagen interpretation was more than a theory. It was a mirror held up to the human mind. It reflected our limitations, our curiosity, and our desire to find order in the unknown. Bohr's genius lay not in providing answers, but in showing that the questions themselves are what give life to discovery. Through his philosophy, he invited humanity to embrace the paradox, to see certainty and uncertainty, knowledge and mystery, as partners in an eternal dance. When Bohr spoke of the quantum world, he spoke as if of life itself, unpredictable, interconnected, and full of wonder. His interpretation told us that reality is not fixed but alive, unfolding only when we engage with it. In that truth lies a lesson far beyond science, that every act of observation, every moment of awareness, is a creative act. Through his vision, Bohr transformed not only physics but the human understanding of existence, teaching that to observe the universe is, in some mysterious way, to become part of its creation. As the world stood on the brink of a new scientific age, Niels Bohr's influence extended far beyond the laboratory. The seventh keynote of his story reflects the legacy he left behind, not only through equations or atomic models, but through the transformation of how humanity understood nature, knowledge, and even itself. Bohr's work had ignited a fire that spread through generations, shaping the path of modern physics and influencing minds across every corner of science. His institute in Copenhagen had become the spiritual heart of quantum mechanics, a place where curiosity reigned supreme and young physicists arrived with dreams of unlocking the secrets of the universe. In the decades that followed his discoveries, Bohr's name became synonymous with the dawn of a new way of thinking. He was not merely a scientist but a philosopher of nature. To those who met him, Bohr was a man of contradictions. Humble yet commanding, cautious yet daring, often pausing for long silences as if measuring every word against the infinite complexity of truth. But behind that quiet exterior was a restless intellect that never stopped questioning. He understood that science was not just about finding answers, but about framing better questions. He believed that progress in knowledge came not from certainty, but from doubt, from the willingness to explore the unknown without fear. Bohr's influence stretched far beyond quantum mechanics. His idea of complementarity, the principle that opposite truths can both be valid depending on perspective, became a universal concept, applied not only in physics but in biology, psychology, and even social sciences. He taught that reality could not be captured by one viewpoint alone, that understanding required balance between opposites, just as light could behave both as a wave and a particle. This idea, so deeply philosophical, transformed how people thought about knowledge itself. It reminded humanity that truth was often complex, layered, and shaped by how we looked at it. During the Second World War, Bohr's life took a dramatic turn. Being of partial Jewish descent, he found himself in danger under Nazi occupation. In 1943, he escaped Denmark in a daring night journey across the sea to Sweden, and then to Britain, before finally reaching the United States. There, he joined the Allied scientific efforts that would culminate in the Manhattan Project. Yet Bohr's purpose was never destruction, it was understanding. He saw with great sadness how the power of atomic energy was being directed toward war. He pleaded for openness among nations, warning that secrecy and rivalry in science could lead humanity into catastrophe. After the war, Bohr became a passionate advocate for the peaceful use of atomic energy. He believed that the same discoveries which had revealed the secrets of the atom could also serve as a bridge toward unity, not division. He wrote letters to world leaders, calling for what he termed an open world, where scientific knowledge would be shared for the benefit of all humanity. In his eyes, cooperation, not competition, was the path to survival in an age of nuclear power. Though not all his appeals were heeded, Bohr's voice carried a moral authority that resonated far beyond his time. He had seen the atom's heart, and he knew both its promise and its peril. As the years passed, Bohr continued to guide new generations of scientists. Many of the greatest physicists of the 20th century had once been his students: Werner Heisenberg, Wolfgang Pauli, Lev Landau, and countless others. They would carry his ideas forward, expanding quantum mechanics into new realms and applying its principles to technology, chemistry, and information science, the digital age, quantum computing, and even the theories that describe the universe's earliest moments all trace their intellectual roots back to Bohr's vision of the atom. The Copenhagen interpretation had become more than a model, it was a foundation upon which modern physics still stands. But Bohr's legacy was not confined to academia. He had changed the way ordinary people thought about the universe. Through his insights, the atom was no longer a simple miniature solar system. It was a symbol of mystery, of the unseen forces shaping reality. His philosophy encouraged humility before nature, reminding humanity that even the smallest particles contain endless wonder. He had revealed that uncertainty was not chaos but structure, a deeper order that humans could glimpse but never fully grasp. In his later years, Bohr became a revered figure in world science, not for his fame but for his wisdom. His home in Copenhagen remained open to visiting scholars, where discussions of science, art, and philosophy flowed late into the night. He never sought recognition or titles, he sought understanding. When he was awarded the Nobel Prize in 1922, he accepted it not as a personal victory, but as a tribute to human curiosity itself. Every idea, he would say, was the result of many minds thinking together. In a visual documentary scene, we might see the old Bohr sitting quietly in his study, surrounded by books and papers, the faint ticking of a clock marking the passage of time. His gaze would drift toward the window, where sunlight filtered through, illuminating the quiet serenity of his surroundings. In that moment, the viewer would feel the immense peace of a man who had looked into the heart of matter and found there not just particles and waves, but a reflection of life's own duality: order and chaos, certainty and doubt, knowledge and mystery. Bohr's final message to the world was one of harmony between science and humanity. He believed that understanding the universe required compassion as much as intellect, that knowledge without wisdom could destroy, but knowledge guided by empathy could enlighten. He left behind more than theories. He left a way of seeing the world, one that continues to inspire scientists and thinkers to this day. In the end, Bohr's genius was not just in unlocking the quantum atom, but in revealing the spirit of discovery itself. He taught that truth is never absolute, that observation and understanding are acts of participation in the universe's unfolding story. His legacy endures in every quantum experiment, every philosophical debate, and every human attempt to grasp the unknown. The man who once looked into the atom's mysterious core had shown humanity that, at its heart, science is not the study of things, it is the study of ourselves.